Hello, class. Here's our first example with applying a free body diagram. A free body diagram is drawing force vectors on your figure as represented by the pink, reddish arrows that you see. In this problem, a friend has given you a special gift, a box of mass 10 kilograms with a mystery surprise inside. The box is resting on the smooth, frictionless, horizontal surface of a table. For part A, we're going to determine the weight, which was represented by Fg, of the box, and the normal force, which is represented by Fn, exerted on it by the table. The equation for weight is mass times acceleration of gravity, which is mg. Plug and chug, and then you get 98 newtons. For the second part of this problem, we want to solve for the normal force, the force of the table pushing up against the box. With most force problems, we want to start with some of the forces in one particular direction. In this case, our direction is in the y direction. The second step is to consider if the object is accelerating in that particular direction. In this case, the box is at rest on the table, so no, the box is not floating in the air nor falling through the table. So we want to set the sum of the forces in the y direction to 0. The next step is to plug in the values on the left side of the equation for all of our forces pointing along the y direction. Force vector arrows pointing up will be positive, and the force vector arrows pointing down will be negative. In this example, we have a normal force pointing up and weight represented as mg pointing down. To solve for the normal force, all we have to do is rearrange the equation to have Fn equals mg. Plug and chug to get 98. Now for part B, your friend pushed down on the box with a force of 40 newtons. We need to determine the normal force exerted on the box by the table. Again, we start with some of the forces in the y direction, which is still 0 because the box is not moving. Look at the left-hand side of the equation. We have 3 force vectors. Normal force pointing up, weight, which is mg pointing down, and 40 newtons caused by the hand also pointing down. Again, rearrange the equations to solve for the normal force. Plug and chug to get 138 newtons. Notice that the normal force caused by the table pushing up increase because it has to balance out a greater force pushing down on the box for it not to fall through the table. For example 4-6, a friend has given you a special gift. For part C, if your friend pulls upward on the box with a force of 40 newtons, what now is the normal force exerted on the box by the table? Again, sum of the forces in the y direction equals 0. Now we have a positive 40 newtons pointing upwards, and a positive normal force, and then a minus mg. The equation is rearranged to solve for the normal force. Plug and chug, and we get 58 newtons. In this example, the box is now accelerating upward. So what happens when a person pulls upward on the box with a force equal to or greater than the box weight? For example, let's let Fp equal 100 newtons. This time we have some of the forces in the y direction equal ma, and not 0 because the box is accelerating upward. The force vectors on the left hand of the equation, we have positive Fp pointing upward, negative weight pointing down, all equaling ma. The equation is rearranged to solve for acceleration. Plug and chug to get 0.2 meters per second squared. The next example is we have a 65 kilogram woman descends in an elevator that briefly accelerates at 0.2 g downward. She stands on a scale that reads in kilogram. For part A, during this acceleration, what is her weight and what does the scale read? The definition of weight, again, is mg. So all we have to do is plug and chug, and we get 637 newtons. Now, for the next question, we need the value of acceleration, which is just 0.2 times 9.8, and that gives us a value of negative 1.96 meters per second squared, because the acceleration is pointing downward. On a side note, did you guys notice that the elevator is also moving down? So the velocity and acceleration are both pointing downward, which means that the elevator is increasing speed as it moves down. With the elevator accelerating downward, we have the sum of the forces in the y direction equal ma. Our forces for the y direction is a normal force pointing up and weight pointing down. Solve for the normal force. And factor out mass to simplify the equation. Note that this step is not necessary. Plug and chug, and we get 510 newtons. Notice that I plugged in a negative value for acceleration. Now, if our scale is measured in kilograms instead of newtons, just divide your normal force by 9.8 to get the value in kilograms for a mass reading on the scale. For now,